talk about the UI iceberg, with the mental model of the system being the much larger part below sea level. One example of this kind of failure is the amnesiac website that doesn't present a consistent view of state. I get very frustrated. with sites like this that give us often complicated forms to complete and then erase all of the entries we've made if there's a single validation error. This is a very poor user experience and very poor user interface design, however visually stunning the pixel painting might be. Let me think that you can often spot software that's been developed with the UI team separate from the development team. I recently opened a new bank account and the user interface uses an icon to represent the accounts that I hold. But depending on where I am when I click the icon, I get completely different views and responses, and seemingly rarely the one that I'm hoping for. This is certainly bad user interface design, even though they've clearly spent a lot of time and money to make it look very pretty. UI UX design is part of the design of the software. It's not part of the specification, and it's about an awful lot more than only visual appeal. UI as a screen mock-up is also not even close to detailed enough to specify features. It works poorly as a specification of what we really want of the system because it misses so much in terms of the interactions, which is the thing that really helps users to build and maintain their mental model of how the system works. I think that this problem is caused by confusing user interface with user need. They are not even close to being the same thing. As a user of a bookstore, I want to be able to find books I like and buy them. This is a requirement. The decision to achieve that via search field, a preview panel and a shopping cart is not a requirement, it's a design choice. It's part of the design of the solution. This may be a good or bad choice depending on the context, but it's still a design choice. It's a poor choice, for example, if we're trying to build a voice-activated system. But find books and buy them is still correct as a requirement. In software development, the job of requirements is to define what the system needs to do, not how it does it. How the system solves the problem is part of our job, the optional part, of us discovering suitable solutions. And the best solutions are achieved when we can iterate towards them as we learn more. So it's best if we can clearly state the goal that it is that we're trying to achieve rather than any particular solution on the way to that goal. Mistaking UI designs for requirements limits our ability to change things as we learn more, and so reduces our chances of us finding good solutions. The most common place for UI design within an organisation structure that I see looks something like this. A product owner works with the UI teams to mock up a UI of some kind. The UI is then passed over to the development team as the definition of a feature, and the development team are tasked with making the UI work. This has several problems. First, as I've already described, this is how you end up with maybe pretty user interfaces but terrible usability. The other problem, though, is that you also build bottlenecks into the development process and so limit it easy for the user to buy books. What we'd prefer to happen is that when the developer starts to make the UI work and finds that raises lots of unanswered questions, like which values would it be sensible to keep in the form if validation fails at this point, they can either ask the question of someone else or, even better, understand what they're building well enough to imagine using the system for themselves. Also great UI designers. So it isn't that we don't need people with design skills, we clearly do. But software developers are usually also fairly sophisticated users of software in one form or another. So there is usually a lot of inbuilt tacit knowledge and experience that even and helps the stream-aligned team feature, and through the process coaching them is an organisational choice. All of those things are linked in the decisions overall. It's all part of supporting that mental model that the user holds of the systems that we build. I think it's a big mistake to attempt to What is it that distinguishes engineering from other disciplines? Day to day, what changes when you begin to learn to think like an engineer? Actually, I think that one of the pioneers of software engineering, in fact the first software engineer, a mental tool if you like, and somewhat irrespective of engineering, nitrogen as well as fuel burn, acceleration and so on. So they added in. She pointed out that when a system was in a particular mode, an astronaut had only. When I write a function, what will happen if the parameters that are passed into it are wrong? Would my code be better if I checked the inputs before I acted on them? If part of my system fails, does everything fail together, or would it be better if I designed it to fail safely, offering a progressive degradation in service rather than a catastrophic halt? Maybe I could build my system so that each part was somewhat isolated from every other, so that some parts could carry on doing useful work while broken parts recovered. I'm pretty sure that that would be a better system than one that just crashed. We get much deeper insight into the systems that we build when we start to think about how things might go wrong and design those systems.
Apache Kafka is a distributed streaming platform for building real-time data pipelines and streaming applications at massive scale. Originally developed at LinkedIn, Kafka was created to solve the problem of ingesting high volumes of event data with low latency. It was open sourced in 2011 through the Apache Software Foundation and has since become one of the most popular event streaming platforms. Event streams are organized into topics that are distributed across multiple servers, called brokers. This ensures data is easily accessible and resilient to system crashes. Applications that feed data into Kafka are called producers, while those that consume data are called consumers. Kafka's strength lies in its ability to handle massive amounts of data, its flexibility to work with diverse applications, and its fault tolerance. This sets it apart from simpler messaging systems. Kafka has become a critical component of modern system architectures due to its ability to enable real-time, scalable data streaming. Let's discuss some of Kafka's most common and impactful use cases. First, Kafka serves as a highly reliable, scalable message queue. It decouples data producers from data consumers, which allows them to operate independently and efficiently at scale. A major use case is activity tracking. Kafka is ideal for ingesting and storing real-time events like clicks, views, and purchases from high-traffic websites and applications. Companies like Uber and Netflix use Kafka for real-time analytics of user activity. For gathering data from many sources, Kafka can consolidate disparate streams into unified real-time pipelines for analytics and storage. This is extremely useful for aggregating Internet of Things and sensor data. In microservices architecture, Kafka serves as a real-time data bus that allows different services to talk to each other. Kafka is also great for monitoring and observability when integrated with the ELK stack. It collects metrics, application logs, and network data in real time, which can then be aggregated and analyzed to monitor overall system health and performance. Last but not least, Kafka enables scalable stream processing of big data through its distributed architecture. It can handle massive volumes of real-time data streams. For example, processing user click streams for product recommendations, detecting anomalies in IoT sensor data, or analyzing financial market data. Kafka has some limitations though. It's quite complicated. It has a steep learning curve. It requires some expertise for setup, scaling, and maintenance. It can be quite resource intensive, requiring substantial hardware and operational investment. This might not be ideal for smaller startups. It is also not suitable for ultra-low latency applications like high-frequency trading, where microseconds matter. So there you have it. Kafka is a versatile platform that excels at scalable real-time data streaming for modern architectures. Its core queuing and messaging features power an array of critical applications and workloads.
Hey, Tim Berglund with Confluent. This is the fundamentals of Apache Kafka within the course called Fundamentals of Apache Kafka. So we're really going to get into the fundamentals here. This module, you're going to develop a mental model of what Kafka is. When we're done, you should be able to identify the key elements of a Kafka cluster and have some idea of what the basic responsibilities of each element are, explain what a topic is and how it's composed of partitions and what segments are, and that basic sort of storage model of Kafka. Topics are what you're going to spend a lot of time thinking about when you're actually building applications on Kafka, so we want that to be pretty solid by the time we're done. Now, it is a fact of the world that lots of things happen in it. There are many events produced, and no matter what sort of industry you're in, like the industries you see pictured here, all of those things are producing events all the time. And Kafka's job is to manage and process those events. So, to get data into a Kafka cluster, we have a thing called a producer. A producer is an application that you write. So that Kafka box there, that's either a Kafka cluster that you're operating, or maybe it's a Kafka cluster in a cloud service where you don't know too much about the operational details, but you know the service is there and it's reliable and you know how to connect to it. That Kafka cluster is that thing out there. Your job is to write programs that put data into it and read data out of it and do useful things with them. So all of those sources of events, we see connected cars, financial transactions, things happening in hospitals, boxes being shipped around the world. All of those are potential sources of events, and some producing application is aware of those events and takes an action to write those events into a Kafka cluster. And after they get written, the Kafka cluster says, okay, got it, sends an acknowledgement, and the producer moves on. Now, what's in a Kafka cluster? Let's break that down a little bit. It's made up of things called brokers. Now, if you will, just kind of set the Wayback Machine for maybe 10 or 15 years ago when computers were things that you saw and they were in a data center and you could like maybe go to that data center and it was this metal box with blinky lights and fans and that sort of thing. If you could imagine that helps make this a little crisper here. Those individual servers, those are kind of what brokers are. There's a Kafka process running on each one. Each one has its own disks. That's important. Every broker has its own local storage. Those brokers are networked together and they act together as a single Kafka cluster. When producers produce, they write into those things that are brokers. Now, if you're using Kafka in the cloud, you're hopefully not going to be thinking about brokers too much if you're using a fully managed service. There are brokers that are out there. You know that's true. They've got their own local storage. They've got some retention time set on the data that they're storing. That's maybe 5 minutes or maybe a month or maybe 100 years. They've got some amount of time they're going to keep those events around. But in the cloud, of course, we don't think too closely about brokers. Those are a thing that's abstracted away from us. But it's true, and you should know this. Every Kafka cluster is composed of these things called brokers. And we never quite know how to refer to those. Are they machines? Are they servers? These are all sort of old words. They might be containers. They might be VMs somewhere. And I'll skip that for the rest of this course. I'll probably just call them machines or servers or some kind of legacy term like that, in as much as we're talking about brokers, just so you kind of have an idea what I mean. Now that data gets written into that cluster, it's stored on those disks inside those brokers, and of course we want to read it out. We do that with a consumer. And this consumer is a program you write. That Kafka cluster, those brokers, that's infrastructure. Somebody manages that infrastructure, operates that cluster. Ideally it's a managed service in the cloud, but what you write is the producer and the consumer. You put data in and you read data out. And it's reading data that frankly usually gets pretty interesting. This is where a lot of the work happens on the consume side. What the consumer does with that data, well, that's up to the application itself. Is it generating a report, feeding a dashboard? Is there some other process that it's sending that process data to? Often a consumer will also be a producer and put its results into a different place in Kafka, that transformed data. But these are the fundamental parts of Kafka. You have a producer, you have the cluster itself, you have a consumer. And that model, those three pieces, everything that ever gets built with Kafka conforms to that model. Maybe you won't see the consumer and the producer directly if you're using something like Kafka Streams or KSQLDB, which we'll cover in a later module. You don't think about producing and consuming, but they're always there. These are the fundamental components of Kafka. So let's look at that again and add a component. We've got our producers there on the left, that Kafka cluster in the middle. Those producing applications are writing into the cluster. Then you've got the consumers, they're reading from the cluster. What's that thing on top? Well, that's a Zookeeper ensemble. As of the time of this recording, Kafka uses Zookeeper to manage consensus on a few pieces of distributed state. There are a few things that all of those brokers need to agree on. They need to have some consensus story on what is true, and Zookeeper is good at doing that. Now again, as I said at the time of this recording, there's an initiative underway called KIP 500. That's Kafka Improvement Proposal 500. That itself has spawned a number of child KIPs and a whole bunch of work to remove Zookeeper from Kafka completely. So at some point after this recording, that will not be there anymore. So it may be that you look at Kafka and the current release you're using, and maybe you see this video and you say, well, there's no Zookeeper there, and that means a new day has dawned. So there's a lot of work to get that done, and that work is ongoing. But for now, Zookeeper's doing a great job being a distributed consensus manager for the cluster. Producers and consumers are decoupled from one another. So a consumer doesn't know anything about the producer that produced the data that it's reading. Likewise, when you produce data, you're not sending it to a particular destination. You're sending it to a structure inside the Kafka cluster. That's called a topic. You're producing that data to a topic. We'll cover those more in a moment. But you don't know anything about who's consuming from that topic. And that decoupling is intentional. That means that there's a whole category of state information between producer and consumer that is simply never managed. Producers write data in, consumers read data out. That also means that producers can scale. I can add producers that write data into a cluster without the consumers knowing. I can add consumers that are reading a kind of data that has long existed. Maybe I've got this long history of records of sales transactions in my cluster. I add some new fraud detection algorithm. Well, that's a new consumer. None of my producers need to know. They can fail independently. They can evolve independently. They're decoupled, so they don't need to know about each other. Revisiting Zookeeper for a moment, what does it really do? Well, authorization information, that's access control lists, those are stored in Zookeeper. The management of failure, so when a broker fails, there are going to be various pieces of a topic that that broker is the leader for. They're replicated in other places in the cluster, but the way that replication is organized and who's in charge of each replica and that sort of thing, that is managed by Zookeeper. So when a broker dies and the cluster has to decide who gets responsibility for the data it was managing, Zookeeper participates in the election of new leaders for those things. So that's basically what it does. Little bits of metadata, failover, leader election, access control lists, that stuff is all currently in Zookeeper. I've used this word a few times, topics. Now I want to really give you a definition of what a topic is. A topic is a collection of related messages or related events. You can think of a topic as a log, as a sequence of events. Now there are some exceptions to that. I'm going to unfold some concepts here that help you manage those exceptions, but for right now, just think of it as a sequence of events. A topic is this list of things, and when a producer writes a new one, it just puts it on the end, and the previous ones are kept. I can have any number of producers writing to a topic. I can have a producer writing to multiple topics. Likewise, many consumers can consume from a topic. All of those relationships are end-to-end. There isn't a theoretical limit on the number of topics. There's a practical limit on the number of what are called partitions. We'll get to partitions in a moment. But topics by themselves, it's not like you can only have 50 and then you need to add nodes or anything like that. You can really have conceptually as many as you'd like. And I did say partition, didn't I? So I better tell you what that means. Now, here's a cluster over on the left. It's got a number of topics in it. Let's zoom in on topic C. Now, that topic is a log, and it's a durable log. It's persistent, which means what? It's going to be stored on disk somewhere. And the broker that partition lives on, well, that's just a computer at the end of the day. And if you're writing messages into that topic and reading messages from that topic, that's work, I/O and computational work that computer has to do. None of these things scales forever. You can't have storage scaling forever, and you can't have that pub sub activity on that broker scaling forever. So you might want to break your topic up into pieces. We call those pieces partitions, and then be able to allocate those partitions to different brokers in the cloud. Cluster. This is key to how Kafka scales. I can take a topic, partition it, and allocate each partition to a separate broker. So when I said a topic was a log, and I kind of put a little asterisk on that, and there's an exception to really what that means. Formally speaking, a partition is a log. So every partition has strict ordering. When I produce to a partition, I put the message on the end of the partition. That's the only place I can put it because it's a log. I can't disturb any of the previous messages. They're all immutable events. I just put things on the end. And so that is a log, and the events in that log, that partition, are strictly ordered. A topic having been broken into partitions, you may not have strict ordering over all of the events in the topic, so you've always got ordering within a partition. And if you want to look at an implementation detail, really drill down into what a partition is, on an individual broker, that log file is going to be represented by multiple log segments. Those are individual files on disk on that broker, and it's really a set of a few files. There's some indexes and things like that. So that segment is a thing that exists on disk on the Kafka broker, and each partition can be broken up into multiple segments. Usually, unless you're deeply involved in hands-on administration of a Kafka cluster, you're not going to think about segments so much. But you do have to think about partitioning as you think about how to model data in topics. It's very important. Let's look at that again. In color. If you can see those colors, topic A is green, topic B is, it's kind of a mustardy orange, and I want to call C sort of a cornflower blue. And you're welcome to correct me in the comments if you think any of those color names are wrong. But this cluster now has 4 brokers. We're calling them 101, 102, 103, 104. And you can see how the partitions of each topic are broken up. So topic A has partition 0, 1, and 2. You see partition 0 is on broker 101, partition 1 is on partition 102, partition 2 is on broker 104, and none of topic A is on broker 103. I won't go through all of those, but you can kind of pause the video if you'd like and look through that diagram and see how those partitions are distributed. The cluster does that automatically when a topic is created, by the way. It makes decisions about where those partitions are going to live. What a Kafka cluster doesn't do is keep track of the size of those partitions and move them around if one broker gets overloaded as topics get created and destroyed. Loading, of course, does not stay constant. So this is functionality you'd have to add yourself to keep those things balanced. There are parts of Confluent Platform that will help you do that, make that automatic. And of course, if you're using a managed Kafka service, this sort of thing is a thing that you know vaguely. There is a team of highly skilled software developers and site reliability engineers who are making sure this kind of stuff works for you, and you don't have to, right? You've probably written to a log file at some point, or at least read one, and in time up till now, and those are immutable after offset space. So that's a real thing. You can actually find that out when you produce a message, when you consume a message. The API, you can poke into things and it'll tell you, oh, this ended up being offset such and such, or this was offset such and such. You usually don't need to know, but it's a real that's now. Of course, you'd like them all to be caught up, right? Everybody wants to be kind of close to the events that are being things that you are going to think about the most are the key and the value. So you'll get the wall clock time at the time that you, I don't care what time, partitions. Now, as a developer using Kafka, you're thinking about topics all the time. You're creating a topic, you're thinking about the schema of a topic, what kind of, and there can be many, the producers can take place, but other module that lets you access Kafka if somehow you're using a language that doesn't have library support, or if you just don't want to use that native language support, you can use the REST proxy. And of course, there's a command line free, and there are some exceptions and interesting ways to configure that, but that's basically what's going to happen. You're going to load balance in a round-robin way. Partitions always stay even all the time. And this is the last offset or offset topic. The group, that's kind of the degenerate group. Let's come back to the same architecture diagram that describes every Kafka system you're ever going to build. You've got producers that write data into the cluster.
What's going on, guys? Assalamu alaikum. For a couple of minutes, couple of hours, couple of days, or even forever. Whereas in a traditional message queue, the message multiple nodes. As I said, it's durable, so you can store it for hours, days, partitions for it. Open up the application folder and then go to pom.xml, and in here need to have the configuration that we can pass to a, and this comes from Kafka clients producer dot, and then have a look. We can basically specify a bunch of configuration in here, but the one that I'm interested is the bootstrap. Oops. So bootstrap service, comma, and then the value will be bootstrap and then service. I also want to define the serializer. It didn't work. So the template also will be of type string and then string. So this is using generics. And again, if you were to send, for example, a custom object, this will be that custom object data type. So let's just say here Kafka template, and inside of this Kafka template, I want to return new and then Kafka template. And Kafka template, if I press command P in here, takes the producer factory. Now this producer factory, let's just instantiate it as a bean. So at and then bean, and let's take this in here, command C, and we're going to paste it inside here. And so this is using dependency injection now, and then pass the factory inside, and job done. And last but not least, so that this works, we need to say at and then bean, and there we go. Now that we have the
What are Java beans? This is a term you'll hear to a convention. These class and should implement from the.
What's up, friends? My name is Dan, developer advocate for a class, right? If so, you've created a Spring Bean. Congratulations. So if you have a Spring Bean is just an object that's managed by the Spring IOC container along with some metadata. Now the IOC container, the application context, just this big pool of, right? What are the group to do? I'm going to go ahead and get started, and we're going, and let's say this might be something like a constructor to, nope, that's not what I wanted to do. They make it very easy to do the right thing. In this case, I don't want to do that. So here, use case, it is not best practice, and it description below if you want to go ahead and check that out. But we do not want to do this. Here in IntelliJ, if I go ahead and run this application, there is a little helpful tool here. So where is that? Let's say Spring, and when Spring is in there. All right, and as we do that, we get the beans in our application. So we have our beans application, and our post is the first one. If we look at component, you can see by the documentation here that it says this indicates that an annotated class is a component. Such classes are considered as a bean post service. I can't auto-wire one of those in. I don't know what post service is. So that's why when we annotate this with at component, it knows what that is, and it can auto-wire this in for you. Now you may see code or older code that has the at auto-wired annotation on it saying, hey, Spring, auto-wire these arguments in for me. If there is only a single itself is annotated with at application. application context. All right, so I'm not sure if you did load posts. All right, what we want to do is we want to use something like a REST template to call out to a third-party service. Now, REST template, we could create an instance here in our class, but this is probably something that we'll use throughout our application, so we may just want one. We usually find them in application context. So let's say that we are going to return our instance of our REST template. Applications is after the application starts and after the application context has been created. So we could do some things in here. We can say hello, and let's go ahead and use an emoji just for fun. And here, but if we go ahead, annotations. So if we look, this is a functional interface. This means that it is a candidate. Application starts, and after the application, we see your parameter, and as you can see, that gets wired in for us by Spring, and then we can use that. And I do this a lot in my applications. Is I will create a. So if we look in here, we see configure and bean definitions. So runner. So and if we say var args things in here, we can say we go ahead and remove app bean. It's not really a big deal. So I'll leave some resources in the description below. Again, I have a Spring Boot crash course that's almost 4 hours long. We cover that and a whole lot more. And I'll leave some links to a article that I wrote.
Well, welcome everybody. Thank you all for joining us today. I know for people when they make that shift.
on reading code better. Reading code is code reading is not taught or practiced or
the producer configuration.
Attempting to shame someone publicly for their safe, legal, and consensual private life is some dark shit. Yeah, people do kill themselves after all. Weird. That almost feels like a weird tacit threat. Just saying that. I mean, I was like really on his side, but it's just it's like a weird threatish type thing. Like that one's weird. Okay, that's weird. I just say, I don't know how to like. I am. Challenging projects every programmer should try. This should be a good one for you guys because every single day I get asked, what should I do? So let's find out. Challenging projects every programmer should try. This post has spurred a lot of discussion on Hacker News and Reddit. Does that just mean people called you an idiot? I'm pretty sure that's Reddit. You just got dumb. Interested in? Then it doesn't matter. Draw like 10 items on a piece of paper and throw a dart at it. Like, shut the hell up and just pick something, okay? There's no single project I'm going to be able to help you with if you don't even know what you're interested in. If you know what you're interested in, then you don't have to ask me. I'm just waiting for all the C# Andes to be like, oh, trust me, it's the best. Just throwing that out there. That one sounds probably the most tedious of them all because you can't use built-in text box component from your favorite GUI framework. This is actually great. This actually, I think, is probably the best suggestion yet because you're going to actually run into a lot of data structure. This is just fantastic. Tried to just a lot of that was a rope, but is the whole thing just one big rope? Oh, that rope. Yeah, it's called a rope strings. Right? Look at that. See, ropes that stays in place. I did work, dude. I snuck away and I did a little bit of multi-threaded programming just because I have to do a little bit of programming every day. Okay, shut up. Anyways, so I click here. This is sometime in the past, right? And let's just say I put in that. Look at what I just created. I created 2 different branches. This branch, which is now my head, but this was my previous branch. What happened if I go here and do more and then do more? And now we have this. What happened if I go back and I jump to this one and I go here? I mean, it's a crazy tree. Undo redo is crazy. It's why you can't just control Z all the time. If you don't have an undo tree, you'll just lose work. It just goes away because you can't do it. Why can't it be linear? Nice. Okay, we're in. We're so in. We're so in. Let's go. We're so in.
Dear functional bros,
at least, what, how many of you type 1 in the... You know, okay? Oh, you can construct it. But goodness gracious. Please. Nice. Okay, we're in. We're so in. We're so in. Let's go. We're so in.
Dear functional bros, I see you, I hear you, and I love you. Functional programming is awesome, but functional programmers are bad marketers. Talking about currying, your monads, binding functors, so many words. I'm not sure anyone truly understands what all these things mean, because they really lie on some spectrum between the math of category theory, lambda calculus, and their specific mapping to different language implementations. But still, I do understand the beauty of it. The concept of a function is so pure. You have this elegant thing that takes an input and gives you an output. And no matter what, the same input always gives you the same output. The key thing that ensures that it gives you the same answer always for infinity is that there's no side effects. There's no state. No thing inside of the function that isn't directly derived by the input. Once you introduce state, the outcome of the function can vary based upon that state. Honestly, most programming paradigms are really just different takes on how you manage state. It's all about state. So let's talk about what functional programming is, why it kind of sucks, but why adding a little bit to your code is awesome. Functional programming takes one extreme side of this state opinion. It's about writing programs based upon one core concept. There shall be no state. You have inputs which are transformed into outputs. In order to get stuff done, you compose and connect functions to other functions, hooking up their inputs and outputs together into one big long chain that achieves the goal of the program. But you don't have objects or structures in memory that you mutate to track what's going on. In this absolute pure world, where you want to write functions with no state, this also means that you're not allowed to mutate variables. So this means if you were to set a value, you cannot change it again. This means conventional iteration loops like for and while are impossible. If you think about a for loop or while loop, it requires you to mutate some state, at least some variable that's tracking how many times you've iterated. So how do you do a loop in a pure functional way? The answer with functional programming is usually, well, more functions, when all you have is a hammer. This is the part that we want to repeat over and over again. So we'll just pull that part out to a function. So now we need to replicate the three parts of the for loop. The key thing that the for loop does is increment the index variable so that the body gets rerun with each index. So we need an equivalent of incrementing index and rerunning our body inside of process receipt. Since we can't mutate index, you can imagine us creating a new variable, next index, which contains the next index we want to process. But now we want to repeat this section again. So we'll need to call process receipt again. So now, if you were to call process receipt, let's say with an index of 2, it would print the merchant from index 2, then recall process receipt with index 3, then 4, etc. But as it is now, it'll keep calling process receipt forever until it goes beyond the size of the receipt array, causing an error to be thrown. And this is where the second part of the for loop comes into play, the condition. We only want to execute the body if the condition is met. Otherwise, we do nothing and move on. So we'll move that condition down into our function where we only do anything if our index is still in range. You can see when we run the program it works like before. It increases the index beyond the size of the array, and we still call our function. But in this case it fails our condition and we do nothing. This breaks the recursive loop and all our functions return. Recursion is just a fancier form of iteration. And finally, we have our last part of the for loop, which is where we set our starting point. This just represents our first call into our recursive loop. So now we've completely converted our loop to be done in the more functional way. We can also remove any unneeded variables to make our code more concise if we wanted. Of loop. So now we've completely converted our loop to be done in the more functional way. We can also remove any unneeded variables to make our code more concise if we wanted. Okay, this is pretty simple and just logs each and this is pretty simple. We can also remove any unneeded variables to make our code more. We can also remove any unneeded functional way. We can also remove any unneeded variables to make our code more concise if we wanted. Okay, this is pretty simple and just logs each item in the loop. But what if we wanted to do something useful, like finding all the receipts that belong to a particular user, and return them so they can be displayed elsewhere? Well, we can take the user ID as a third parameter, and then check if the user matches. This now only prints the receipt of the merchant if the user ID matches. But instead, we want this function to return the list of matching receipts so that it can be displayed on the web app. We need to somehow return the results of the matching. At each recursive call, we want to make an array with the current receipt at the front and the results from the deeper calls attached to the end. This way we can get back everything in order. But we only want to append the current item if it has the right user ID. Otherwise, we just want to pass through the previous result. So in order to do this, we'll actually get the results of the deeper calls first. And then, if the user ID matches, we'll return the current results appended to the later results. Otherwise, just forward on the later results as is. And lastly, if we've processed the entire list, we'll just return empty results since there's no more results to be had. So now, this function just returns all the receipts for a given user ID, and we'll give it a better name. Thing is, you could imagine this pattern happening over and over again whenever you wanted to find stuff in an array. The only difference between these functions is the condition in the if statement. We could replace all three functions with just one if we instead passed in a function that returned whether or not an item should be included. Let's pull out the condition and move it to its own function. And instead of taking the user ID as a parameter, we'll pass in that function instead. We can call it condition. Or if you want to be a classy fellow, you can call it predicate. Then we just call that function where the condition used to be. And that function tells us whether or not to include the item. Then we can pass our condition, the user ID equals function, into our filter. And of course, we can now rename our function to be a generic filter. Now we can run our beautiful program with our filter and user ID equals function, and wait, we have a problem. Our user ID equals function takes two parameters, the receipt and the user ID to check against. But our filter function only checks against the receipt itself. We don't know the user ID to check against. We could try passing in another value that we could relay into the function. But what if we need more than one, like in the case we needed to check if the total was between a range? It gets a bit awkward. So instead, we're going to get a bit fancy here. Instead of having our user ID equals function take both a receipt and a user ID, we're going to have it take only the user ID that we want to compare against. And it will construct and return a new function that takes a receipt and returns whether it's from the user ID. We then pass in that new function that's been created into our filter. This is a little weird, but what's happening is that the user ID is like a secret extra parameter, which is bound to the function. And this function remembers that value and can use it. The name for this pattern is called currying. Instead of handling the entire operation at once, it returns a function that handles the next part of the operation. The later part has the previous state bound to it. That new, on-the-fly things start to get kinda nice. I'm filtering by user now. Or I can filter by merchant just like this. Or do a more complex check on the total here. We might want to get just the filtered merchant names instead of the entire object. If we devise a new function based upon our loop that doesn't filter based, and if we only wanted to take how this is done is behind the scenes in our fundamental functions. So we've just derived these functional style fundamentals ourselves. But these are also built directly to solve a uniquely American problem in an American way. In the US, when you're in a restaurant, you need to fill a tip manually by writing the tip in total. This is effectively a mandatory fee on your meal enforced by social shaming. Your card is initially charged for the total without the tip, but several days later, the updated total with your hand-scribbled tip will show up on your credit card. The problem here is that no one is really going to check whether their tip was accurately reported. User of the app, helping prevent credit card fraud in your or whose totals match correctly. Sort them by the most egregious discrepancy, and then take the top 10.